Welcome back, viewers, to the 7th lecture of this online series of lectures on the course of Introduction to Category Theory. So, in the previous segment, we proved the second proposition of the 7th lecture, and we have shown that the power set of a given set is isomorphic to a certain Hom set, or a certain exponential object. Okay, we have shown that this Hom set from B to omega is isomorphic to the power set of B. Okay, this is what we have shown in the previous segment. And if these two sets are isomorphic to each other, then it makes sense that it makes sense to compare their cardinalities, and we know that they have to be the same as well. So the cardinality of this exponential object is precisely denoted by this, and this is expected to be the cardinality of the power set of B. Okay? And I have already told you in the beginning that this, when the cardinality of omega and the cardinality of B are finite, or one is empty and the other one is finite, then we always have this guy to be equal to the cardinality of omega raised to the cardinality of B, and this is equal to the cardinality of the power set. We know that the cardinality of omega, since it was a two-element set, is just 2. Okay, so 2 to the cardinality of B is equal to the cardinality of the power set, which we already know. Okay, so it conforms with our existing knowledge on the power set. So we just cross-checked it. All right. So now I will give you the formal definition of characteristic function associated with a subset of a given set. Okay. All right. So, characteristic function is defined as follows. Characteristic function. So we already defined it during the proof of the previous proposition, but we denoted it with psi. Now we'll give a proper notation for this characteristic function. So we'll follow this notation from next on. Okay. Characteristic function associated with a subset, with the subset B prime of B, that is B prime being an element of the power set of B, denoted by I of B prime, okay, is a map I sub B prime from B to omega. Okay, the way we define psi, that the one that we used to prove the second proposition, defined as, check that this one is exactly the same as psi, I sub B prime B is equal to true if B is in B prime, and false if B is not in B prime. we can combine this piecewise, so the two parts of this piecewise defined function in one statement by using the equivalence like we did earlier, that chi sub b prime b is equal to true if and only if b is in b prime. So we can combine these two parts of this piecewise defined function in one line this way. Okay. Okay. So now this was the definition of characteristic function. So I suggest an exercise for you. Exercise. I'll give you an assignment soon, in a few days. That will be assignment 3. And I'm not sure if I'm going to include it in the third assignment, but please try doing it. It's important for you to do this exercise on page 62. So I leave it, so I write it as a homework. HW. Okay, now I want to go to the discussion on monomorphism and apimorphism. Okay, so what is the goal? Why do we want to do that? Before giving you the motivation of these terminologies, I want to recall some basic definitions from sets and functions that we did in our second lecture. But we want to refresh the memories, so I'm doing it again. Surjective function. So the topic of this segment is the one that we are going to discuss now is monomorphism and apimorphism. Apimorphism. So before doing that, before giving the formal definition, I want to recall the basic definitions of surjective function, injective function, and bijective function. Okay. A function f from x to y, so that x is the domain of the function and y is the codomain. This function is called surjective if for all y in y, whatever element you take from y, there is always a pre-image here. Okay, this is what this is what you write in the following way. There exists an element in the domain such that f of x is equal to y. Okay, it tells you that every element in this codomain has a pre-image, so that the codomain and the range of the function they coincide with each other. Okay. This was the definition of a surjective function. Now, what is the definition of an injective function? Okay. A function, again, from x to y is called injective. Injective if for a pair of elements of the domain f of x equal to f of x prime will imply x equal to x prime. Okay. Let me elaborate a little more on this notation, on the statement to be more precise. So it tells you that in the y set or in the codomain, if you have f of x to be equal to f of x prime, meaning that you have only one point here, then they cannot correspond to two different points in the domain. They have to be the same as well. Alright? This is what it tells you. It means that so there will be a unique preimage for every point. So there is something important here to understand. We can always, so in mathematical logic, if there is a statement A, and if the statement A implies the statement B, then it is not always true that B will imply A, right? It is not always true. But something is true that we can extract out of this statement, which is not A is implied by not B. This statement that we extracted out of our original statement is called the contrapositive. Okay? Contrapositive. So what is the contrapositive of this statement given here? Okay? In order to do that, we have to negate it first, which tells you that x is not equal to x prime, and that will imply f of x is not equal to f of x prime. Okay? So this statement is equivalent to this statement. So it doesn't matter how you state that fact, okay? Either by this statement or that statement, they are equivalent. So this was important about the injective function. Where you'll be using these facts when we'll discuss properties of monomorphism and epimorphisms. Okay, now what is the definition of a bijective function? A bijective function is defined as a function which is both injective and surjective. So a function which is both injective and surjective is called a bijective function. So I write concisely here, surjective plus injective implies bijective. Okay, so that's pretty much it. Now the question, now I address a question, a very important question. Let me write the question. So let me write it here and give a moment to you to think, is there a way one can define surjective and injective functions, surjective and injective functions without referring to the elements, without referring to the elements of the domain and codomain, of the domain and codomain. What does it mean? Means that you see that while we were defining the surjective function, injective function and bijective function, forget about the bijective, because the definition of bijective involves the definition of surjective and injective. So it's sufficient to talk about the subjectivity and the injectivity. So in both the definition we invoked, so we needed the concept of the elements of this domain and the codomain, because these are elements, x, x prime, these are elements from this domain of the function, and fx and fx prime are elements of the codomain. So is there a way we can define the subjectivity and injectivity in an abstract category where we don't have the idea of the elements of the objects, okay? Because in an abstract category we refer to objects and morphisms between them. We never talk about the elements in the objects. It's only done in the in the context of the category of sets, because the category of in the category of sets you have these objects to be sets, and the element you can talk about elements of the sets. Okay, so without referring to the elements of the domains and codomains, we should be able to express the idea of injectivity and surjectivity, and for that reason we need the terminologies of epimorphism and monomorphism. Okay, let me define them officially now. Okay, so I give the formal definition of monomorphism and epimorphism now. Let me give the formal definition of monomorphism and epimorphism. Let a map from X to Y is given, that is f from X to Y be a function. We say that f is a monomorphism f is a monomorphism so if for all set A, so I can choose the set A arbitrarily, okay, for any set A. So whatever I am going to discuss now should hold for any set A. This is what it says. Okay? For all sets A and pairs of functions which we also call parallel arrows, okay? G prime from A to X. So in other words, we have this diagram, okay? We have this diagram. Let me draw this diagram. So initially we have these two objects. We have a map between these two sets. Okay? So of course, the objects are sets in the category of sets. And we have two parallel arrows from this given set, from any set A to the given set X, denoted by G and G prime. So this is the associated diagram for the definition. Okay? If so, what we want any set, for any set A and any two parallel arrows from A to X, if f composed with h is equal to, sorry, f composed with, sorry, I'm gonna use, sorry, two parallel arrows. So what do I do? I change them to be h, okay, and keep them as denoted by h, right? H, and keep them as h and h prime, right? So that has to be corrected to h and h prime. Okay. There were small typos in my notes. I'll correct them. So, so that f composed with h is the same as f composed with h prime, meaning that this diagram continues. You can go from A to Y into different paths. One is via H and then F, and the other one is first through A via H prime and then via V. Okay, there are two different paths, and they should result in the same final element in Y. Okay, this is what we mean by the commutativity of the diagram, which is the fact that F composed with H is the same as F composed with H prime. If this is the case, then we are definitely going to have H to be equal to H prime. Okay. In other words, if H and H prime are unequal, the diagram will not commute. In that case, we say that F is a monomorphism. This was the definition of monomorphism. Now, I give you the definition of epimorphism. We say that F is an epimorphism for all sets if for all sets B, okay, and pairs of function, again two parallel arrows, and pairs of functions G and G prime from Y to B. Now we have another diagram. We have this diagram first, and then we need two parallel arrows from Y to any set B called G and G prime. Okay. And if G composed with F is the same as G prime composed with F, G prime composed with F, this will imply that G is equal to G prime. Right? It means that if this diagram commutes, then we will of course have G to be equal to G prime. In other words, if these are two unequal functions, then the diagram will never commute. If this is the case, then F is called an epimorphism. Okay? So if we take the contrapositivity of this statement, I mean that I want to write a statement which is equivalent to this one. Sometimes for the sake of proof, you need the contrapositive type of statement of the same fact. Then we prove that G not equal to G prime implies G composed with F is not equal to G prime composed with F. Okay? But they are equivalent. Okay? So sometimes for the sake of the proof, it's easier to prove this one. We go for this one. And sometimes it's easier to prove the original statement, I mean the original version of the statement, or original way of stating the fact. Okay? So, or the contrapositive way of the stating the fact. It depends on which one is convenient for you. So look at the two diagrams. For this was the original diagram, original function, and you associate this, you attach this arbitrary set A to the left of the diagram, the original diagram, for defining monomorphism, and for defining epimorphism, you attach this extra piece to the right of the original diagram. Okay? So now we have a final proposition for our 7th lecture. So let me write down the statement of this proposition. The proof is rather long. I'll do the proof. Let me state it first. Proposition 3. we're still in the category of set. Let f be a function then f is injective, if and only if it is a monomorphism. It is a monomorphism. So it tells you that injective functions are synonymous to monomorphism. Injectivity is synonymous to monomorphism. So you see that while we were defining monomorphism, we never invoked the concept of the elements of a set. So that's the good part of this definition. Because you never have to talk about the elements contained in an object. That is very good for the abstract setup of the category. So this is the first part. So it tells you that injectivity is synonymous to monomorphism. And the later part, f is subjective. If and only if it is an epimorphism. So he tells you, the last part tells you that subjectivity is equivalent to epimorphism. Because for dealing with epimorphism, you never have to. So I think I'm running out of space in my cell phone. So I stop here. I'll come back with the proof of the last proposition in the last segment of this lecture. Thank you.